So in this video, we're going to be looking at electrophilic substitution reactions for our aromatic compounds. But before we do that, we're going to look at electrophilic addition from year 1, quickly recap that and compare it to our actual year 2 mechanism of electrophilic substitution itself. Now looking at electrophilic addition, we know that we've got alkenes, and alkenes, they react by breaking their weaker pi bond. Because we've got a double bond in, let's say, a molecule of propene, we've got in here a very strong sigma bond, which isn't going to break, it's unlikely to break. And then we've got in here as well a weak pi bond, and what happens is that pi bond normally breaks and your mechanism starts from that. Now when we look at alkenes, we say that our alkenes in the carbon-carbon double bond, we've got a region of high electron density, where you can imagine it like magnets, where you've got a negative magnet over here or the negative side of a magnet, and what's going to happen is that's going to repel the electrons, the negative electrons in this covalent bond over here. And what that means is that they're no longer going to be slap bang in the middle. Instead, they're going to be more towards one side. And so what we can say is that our alkenes, they can polarize and attract halogen molecules. So in this case, what's happening is we're ending up with a delta negative sign on one side and then delta positive on the other. That's closer to the actual alkene itself. Now that together with our alkene carbon-carbon double bond, we know we've got a pi bond in there. That pi bond is going to break, and that pi bond, when it breaks, it's going to attack one of the bromine atoms. In this case, it's going to be this delta positive one over here. And you've got to think about your arrows going from a region of high electron density to a region of low electron density most of the time. And in this case, right, we have an electrophile, which is a bromine molecule, and we know an electrophile from year 1 again is going to be an electron pair acceptor. So in that case, my first arrow is going to start off touching the carbon-carbon double bond, the pi bond breaks, and we're going to have a curly arrow which shows a movement of a pair of electrons going towards that partially positive bromine. So that's the first thing that I'm going to do, and I should end up with something that looks like that. Now the next thing is that bromine can't have two bonds, because what we've actually done is we've formed a bond between either one of the two carbon atoms over here, either one of the two edges and corners in the skeletal formula of ethene. And what's happened is we formed that bond. Bromine can't have two bonds, one bond must break, and it's going to be this bromine-bromine bond over here, where we end up with a special type of bond breaking, which we know from year 1 as being heterolytic fission. The covalent bond breaks and both electrons go to the same atom. And in this case, we're going to show the movement of a pair of electrons going to bromine by that bond breaking, and the electrons going to this bromine atom over here. You can see my arrow is touching the bromine atom, the head of it, and then the back end of the arrow is going to be starting from the bromine-bromine bond itself, and it's touching it as well. Now that forms a carbocation intermediate, where we've got a symmetrical alkene here, so we don't need to worry about Markovnikov's rule. So in that case, what I end up making is one edge and one corner over here. There's two carbon atoms, but then I'm going to go with carbon 1 having the bromine on it. Doesn't really matter which one in this case, either one's fine, but the other carbon is going to be having a positive charge itself, right? So the next thing is I need to show with another arrow, because I've got bromine left over, and because it's gained 2 electrons, one of its own back, and it's gained one from the other bromine atom, it ends up being bromine as a negative charge. We're going to end up with another arrow, and it's going to go from the lone pair of electrons quite close straight to that carbon atom itself as well, not to the positive charge. And so you can see over here, right, that's our second step done, our carbocation dealt with. We should end up with the following molecule of 1,2-dibromo, and then it's going to be ethane itself as well. Now, one thing to bear in mind that relates to Module 2 applied to Module 4 and 6 is that because we're only forming one product over here, we've actually got an atom economy that's going to be 100% itself. We've got no waste products being formed. It's an addition reaction. All addition reactions are generally 100% atom economy, because we're just adding one molecule onto another. Now looking at the next reaction mechanism, we've got electrophilic substitution. When we look at this reaction mechanism, again we're involving an electrophile because it's electrophilic, and that is going to be an electron pair acceptor. But in this case, it's going to be a substitution reaction, right? We're swapping one atom out for another rather than adding a molecule onto another molecule itself. Now when we're dealing with our aromatic compounds themselves, which contain a benzene ring, they react by an electrophilic substitution reaction, whereas our alkenes, they're going to react in an addition addition reaction instead. Now there's a reason why the reaction mechanism is going to be different, and it's mainly because benzene, right, these pi electrons, they're going to be delocalized, whereas in our alkene they're localized. And so what that means is in benzene we've got a lower electron density compared to our high electron density in our alkenes, and if the electron density is low, that means that benzene can't actually polarize and attract a molecule of a halogen like bromine or chlorine itself, right? Now when we look at polarization, we need to think about having a region of high electron density. In this case, right, with benzene, it's not going to be as high as an alkene, so we don't end up with partial charges on our bromine atoms within a molecule of bromine or any other halogen as well, right? Now we need to use something called a halogen carrier catalyst, which makes our electrophiles more positive. In some cases it makes them completely positive, so rather than having a partially positive chlorine, you actually end up with a full positive charge on the chlorine or bromine or whatever halogen you're really dealing with, and that's what leads to a substitution reaction actually taking place itself, right? Now some examples of our halogen carrier catalysts, they include things like iron chloride, iron bromide, or aluminium chloride or bromide itself. You can kind of see a pattern over here, and you can use either iron chloride or aluminium chloride, whichever one you want, but you do need to be able to interpret these in the exam. Now, how does this mechanism actually happen? Well, look at the benzene molecule that I've drawn over here in the delocalized model. We're not dealing with Kekulé's model over here. We've got 6 delocalized pi electrons in the benzene ring, and they're spread over 6 carbon atoms itself. And what happens is that 2 of these pi electrons are going to go into making a new bond with our actual electrophile itself. And that's what I'm going to show with my first arrow in this general mechanism, where E is going to be my electrophile that's positively charged. I'm going to end up with an arrow that's going to start off touching my actual ring itself over here, and then what I like to do is I like to show the arrow going through the actual carbon atom where we expect to form the bond, which you can see over here in our products itself. Now, if I were to look at that, right, I'm going to end up with my delocalized ring of electrons. That's going to break. It's going to partially break, and what we end up with is an arrow going from there, touching the ring, straight to the actual electrophile itself, and what we end up with is E plus over here, forming a bond to that carbon atom, right? Now, I'm going to draw the outer hexagon, right, to begin with, which is going to look something like this for our benzene ring, and then the new bond that we've formed going towards the E itself, which the positive charge is now satisfied. But we do also have on there a bond to hydrogen, because remember the formula of benzene is going to be C6H6. We've got a hydrogen bonded to each carbon atom, and that's a problem, because that means, right, we need to get rid of that hydrogen, because now, right, you can kind of think of it as having 5 bonds towards that carbon atom that is attached to itself. Now the thing is, when we look at this intermediate now, that is going to have 4 pi electrons that are left over, because the other 2 have gone into making a bond with our electrophile itself out of the 6, and those 4 pi electrons, we need to show them spread over exactly 5 carbon atoms, and this has been the case since 2023, right? Now in this case we call this a horseshoe shape. It's almost like a semicircle. It's somewhere in between, where we've got to show our horseshoe shape, our semicircle, going all the way around, showing our 4 pi electrons spread over these 5 carbon atoms over here. So we've got 1, 2, 3, 4, 5. That's what we need to cover, and we need to cover it exactly. And what I suggest that you do is that you grab a ruler and you hold your ruler against this actual part over here, so you don't go past the line, and it makes sure that you actually stop at the line itself as well. So again, using your ruler, holding the pencil, I want you to do the same thing, where you start off over here and you're going to draw some sort of a semicircle or a horseshoe shape, because it goes over a semicircle, doesn't it? And within that you're going to have a positive charge itself, like so, right? Now once that's done, right, we need to be able to re-establish the actual benzene ring as well, and to do that we actually lose an atom of hydrogen itself. And what we need to be able to show the examiner is an arrow starting off from our actual bond between the carbon and the hydrogen atom over here, because there's 2 electrons, a shared pair of electrons, and they're going to come into our actual positive charge, into our ring itself, towards the positive charge in this case. So if I were to do that, I end up with an arrow that goes like this, and so there's my next curly arrow showing the movement of a pair of electrons. Now what will happen is that our horseshoe shape now closes, and what we end up with is, yes, a molecule of our electrophile attached to our actual benzene ring itself, where the electrophile can change to anything. Now note, because we've lost that hydrogen atom over there, we actually are left with that as a byproduct, and so we're going to leave that H plus. Because it's covered by this little page symbol, I'm going to put it over here. We also end up with that as a product as well. So let's look at some examples then, now that we know how to do an electrophilic substitution reaction mechanism. There's 4 that you need to know. The first one is halogenation, where you take a molecule of whatever halogen you want, your halogen carrier catalyst like you've got over here, and what you make is, right, you substitute a hydrogen for a bromine like how you've done over here, and you actually make the byproduct is HBr. So I've got bromobenzene and I've got HBr here as well. Now in this case, our halogen carrier catalyst is going to be a key condition that we need, like iron bromide or aluminium bromide. If we just had bromine on its own with no halogen carrier catalyst, nothing would happen. Now you need to be able to show how the electrophile is actually going to be generated here, and what happens is you end up with a reaction between iron, and that's going to be bromide. That's the example I'm going for, and that's going to react with a molecule of bromine itself, and what you actually end up with is going to be iron bromide as an ion, so you end up with FeBr, and then it's going to be 4 minus, and then you're also going to end up with your bromine but positively charged. There's your electrophile over there. Now when it comes to your actual mechanism, what you need to be able to show is that you've got bromine, and I like to draw it in a nice position like this, and I'm going to circle the charge so that the examiner knows I haven't missed it out. Now the first thing that's going to happen here is that our ring of electrons is going to break, and 2 of these pi electrons go into forming an actual bond between the benzene ring, one of the carbon atoms, and the bromine ion itself as well. And what we actually end up with is an intermediate, where we've got again our outer hexagon layer, which is going to look like this. We've got that hydrogen still on there, that's going to be lost in a second. We've got bromine on here, and we've got our horseshoe shape again that covers 5 carbon atoms. We've got 4 electrons, 4 pi electrons covering 5 carbon atoms, and a positive charge in the center as well. Now what's going to happen is that this hydrogen carbon bond is going to break. Both electrons, they're going to go into our actual positive charge over here, our ring itself, and what we actually end up with, right, is a molecule of bromobenzene itself, and then we've got our ring being reformed, 6 pi electrons there again, and then we've got bromine hanging off there as well. And don't forget the byproduct, which is going to be the hydrogen ion itself, the H plus ion. Once we've got that, we need to show how our catalyst is going to be regenerated, because remember, the catalyst is going to be unused. It's going to be swallowed up by the reaction, and then it's going to be spat back out, right? It's unchanged chemically, and we've got in this case FeBr, and then it's going to be 4 minus, and that's going to react with the H plus, and what we end up forming is HBr, which is our byproduct over here, and then we also end up forming Fe, and then it's going to be Br3 itself. Now there's our first reaction done and dealt with. Now moving on, another reaction that you need to be aware of is nitration itself. And this is when you add a nitro group, right, onto a molecule of benzene. You swap out a hydrogen atom for a nitro group itself. And the key conditions for this is that you use concentrated nitric acid and concentrated sulfuric acid, and you keep the temperature at 50 degrees Celsius. And the reason why you do that is because if you wanted only one substitution to take place, you would use 50 degrees Celsius. If you wanted more substitutions to take place, you would use higher temperatures compared to that 50 degrees Celsius itself. The byproduct over here in this case is going to be water itself being formed. Now if you were to look at how the electrophile is going to be generated, we take nitric acid, we react that with sulfuric acid, again they're both concentrated, and what we end up forming is NO2 plus. We form on here as well HSO4, hydrogen sulfate ions. We also form water as well. And again, our electrophile in this case is going to be the NO2 plus group over here. So in that case, I'm going to draw my electrophile. I'm going to put NO2, and then it's going to be positive. I'm going to put the positive side on the nitrogen itself, because the nitrogen is what's going to be positively charged here. And what I'm going to end up with is, again, another arrow, and then our intermediate, again with the horseshoe shape, covering exactly 5 carbon atoms, and then my nitro group's attached. I've got a hydrogen atom attached as well, and then our ring is going to be reformed again with these 2 electrons. We've got 6 pi electrons again. Now, if you were to form our product, what we should actually end up with is nitrobenzene. So I'm going to draw my hexagon, and then I'm going to have my circle in it, and then I'm going to have the nitro group there, as well as a H plus as well. Now, we do need to show how the catalyst, which is going to be sulfuric acid in this case, is going to be reformed from hydrogen sulfate ions itself. And so I've got HSO4 minus reacts with H plus, and what we actually end up making is H2SO4. Now, moving on, the next example, we've got alkylation over here. Friedel-Craft's alkylation is what you might come across, and if we were to look at the overall equation again, it uses a halogen carrier catalyst like FeBr3 or AlBr3, and we take a haloalkane, and in this case, right, we're actually extending the length of the carbon chain. We're adding a carbon containing compound, a carbon group, onto our benzene ring itself. The byproduct is the same as halogenation as well. If we were to look at the electrophile though, right, similar type of reaction compared to halogenation, where we take our CH3 Br, right, and then our key condition, which is a halogen carrier catalyst, which is going to be having a FeBr3 or AlBr3, either one, and what you end up with is CH3, and then it's going to be positively charged as well, and then you're also going to end up with Fe, and then it's going to be Br4 minus itself. Now, in terms of our mechanism, again, we're going to have CH3 over here. It's going to be positively charged, and again, a curly arrow going from the ring, donating 2 electrons, going towards a carbon atom, forming a bond. We end up forming, right, again, a horseshoe shape. I'm going to make sure that it definitely covers 5 carbon atoms, which in this case it does, and we have got 4 pi electrons covering 5 carbon atoms over here, horseshoe shape, positive charge, and then I'm going to have my hydrogen. There's 1 bond, and then I'm going to keep the CH3 in skeletal formula just for consistency. Once that's done, the carbon-hydrogen bond breaks. Both electrons go back into the ring, reforming the pi system, and what we end up forming is a molecule of, in this case, methyl benzene itself, right? Now, how does the halogen carrier catalyst regenerate? Well, don't forget, you've also got another product in there, which is going to be the H plus, and that H plus that we've just lost from the benzene ring, that will be mopped up by any FeBr, and then it's going to be 4 minus itself. We reform and regenerate our catalyst, where we end up with FeBr3, and then we also make the byproduct, which is HBr itself there as well. Now, moving on, what about acylation? Again, it's a very similar mechanism, where in this case you use something called an acyl chloride, which basically just looks like a in this case ethanoic acid, but you've swapped out the OH for Cl, and again you use a halogen carrier catalyst and you make the same byproducts as well. In this case, we're going with iron chloride. So again, we're going to have FeCl3, and that's going to react with our acyl chloride, which in this case is called ethanoyl chloride, which is going to look like this. And what happens is that FeCl3 will nab off the actual chlorine itself, and we're left with FeCl4, and then we're left with our electrophile, which is going to look like this itself. Yeah, now once that's done, you're going to end up with your electrophile again in the reaction mechanism, and you're going to end up with that ring breaking. 2 electrons are going to be donated towards that carbon atom over there, and you form a bond. Now, your intermediate is going to be quite hard to draw, but if you follow the normal procedure, in which you've got a hexagon and then you've got a horseshoe shape in that hexagon that covers 5 carbon atoms only, don't go over, don't go under, you're going to have a hydrogen atom over here, but to that you're going to have bonded 2 carbon atoms. There's 1 carbon atom there done, and it's going to be bonded to an oxygen double bond, and you're going to end up with another carbon atom over here as well. It's important to know that the bond is going to be between the carbon that is bonded, double bonded to the oxygen itself. So the bond between benzene and the actual carbon atom is there. Now, if I were to look at that, right, I'm going to end up with this bond breaking. Both electrons reform the pi system. Now, in terms of our product, how to form phenyl ethanol, we have ended up with each carbon atom with 4 bonds. And so we've got this molecule over here. And then again, you're going to have the H+, which is going to be mopped up by our Fe. In this case, it's Cl4 minus. And then you're going to end up with your halogen carrier catalyst, and then HCl in this case, because again we've used ethanol chloride itself. Now, I've got a task for you to do. Feel free to pause the video and have a go at the following. So moving on then, we've got compounds B and C shown below, and they're unsaturated hydrocarbons containing 9 carbon atoms, right? Now compound B reacts with chlorine at room temperature, but compound C requires the presence of a halogen carrier. Now in both reactions, the organic compound reacts with chlorine in a 1:1 molar ratio. Draw the structures of the organic product of each reaction itself. Now with B, we can see the homologous series that it belongs to. It's going to be an alkene, so we end up with an addition reaction, 100% atom economy, both chlorine atoms attached to each carbon atom. So in this case, what we end up with is, yes, our weird transformer looking molecule. We get rid of the double bond, but to one carbon atom we add a chlorine, to the other carbon atom we also add another chlorine atom itself as well. Now if I were to look at C itself, right, in this case with C, I've got a substitution reaction taking place where I swap out one hydrogen for an actual chlorine atom itself, because it contains a benzene ring in there. It's an aromatic compound. We know that it's not strong enough, right, it's not rich in electron density enough to attract and polarize a molecule of chlorine for an electrophilic addition reaction. It uses a halogen carrier catalyst, and so what we end up with is a hydrogen atom being swapped out for an actual chlorine atom itself, right? And remember, you've got one hydrogen here, and then one hydrogen there, so either one of them is fine. And again, because it reacts in a 1:1 ratio, right, we just swap out just one of them only, and there's our product itself. Moving on, feel free to pause the video and have a go at the following. So in this question, we're asked which compounds could be prepared by reacting benzene with an acyl chloride. So again, remember, it's that thing with carbon oxygen double bond, but it's bonded to a chlorine, and the other side we can have any alkyl group that we want. Now again, it says acyl chloride in the presence of a halogen carrier catalyst, and we need to think about each of these structures, right? Because remember, the bond actually forms to this carbon atom over here that is double bonded to an oxygen itself, and to do that we need to look at the actual displayed or skeletal formula itself. So in this case, this bond is going to be going towards a carbon atom, right, and that's going to be bonded to a double bond oxygen, and we've got a hydrogen atom over here, so that looks plausible. If we were to look at the following, right, we've got over here to a carbon atom again, but then this time, right, that carbon atom is bonded to another carbon atom where we've actually got our oxygen double bonded to carbon over here, followed by another carbon atom, so it wouldn't really work for that one. If we were to look at the next one, we've got again benzene. It's going to be bonded to a carbon atom, which is double bonded to an oxygen, bonded to a kind of carbon again. So in that case, right, these two are going to be plausible, this first one and this last one, but the middle one won't be. And the reason why is because we need to have the carbon atom that is double bonded to an oxygen atom directly bonded to the benzene ring itself, right? So moving on, another question here. Feel free to pause the video and have a go at the following. So yeah, going over this one, we've got benzene. It reacts with an organic reagent in the presence of a halogen carrier to form phenyl ethanone. Suggest which reagent could be used. So what I would do is I would actually slice the bond that is involved. I would draw out what's left over, which in this case is carbon, double bonded to oxygen, and then we end up with one carbon atom over here as well. Now we've got a positive charge over here, so we've got to think, what can we replace it with? Well, in this case I would have a chlorine there to make ethanol chloride itself. Nice easy question there. Moving on, feel free to have a go at the following synthesis map, a common question that comes up on different homologous series. So yeah, in the first instance, we've got a molecule of 2-bromopropane, and that's going to be added to benzene itself. So in that case, 2-bromopropane is going to look like this, where we've got a bromine on the second position. If we use a halogen carrier catalyst like FeBr3, we would actually end up with a positive charge on the second position over here. So we know we draw a molecule of benzene, which looks like this, and the bond is going to be formed at the second position over here, yeah? And so we end up with a molecule that actually looks like that. Looking at the next one, we've got a nitration taking place, and it's going to be 50 degrees Celsius, so only one substitution happens. So I'm going to end up with, again, a ring in there, and then I've got NO2 over here. Next one, we've got iron chloride, and then we've got chlorine. We're just going to have a straightforward chlorobenzene molecule being formed from that. The one after that, again, look, it's got 3 carbon atoms over here, and we're going to swap out this chlorine for one of the hydrogen atoms. And so what we end up with is, yes, a molecule of benzene, but we're going to have that bonded to a carbon atom that's double bonded to an oxygen, and then we're going to have 2 more carbon atoms on there as well to complete the chain. So that's 2 more edges and corners, and that's done.